Well, batteries have always been, big interest for me because of all the different hobbies that use batteries that I've been interested in. So, not only for amateur radio, but Jacob and I also do a fair amount of radio control work. And believe it or not, once upon a time when I was working for the Gillette company, Gillette at the time owned the Duracell battery company. So one of my roles was working in Gillette was managing health, human and environmental safety and environmental remediation and so forth. So I got to know a lot of guys at Duracell and had the opportunity to spend a fair amount of time in battery manufacturing plants. So learned a fair amount about alkaline batteries and lithium batteries over the years. So I'll share a few little stories about that as I go through all this. So what are batteries? We know that batteries are devices that store chemical energy so that we can use it whenever we want and release that chemical energy as electrical energy that's useful in our electronics. They produce the power that we need in circuits that, and they run for a certain amount of time. They have a finite life, particularly if they're non-rechargeable. If they're a non-rechargeable battery, when they're done, you can chuck them out. Some batteries, as you know, are rechargeable, but they have a fixed number of times they can be recharged before they build up oxidation products inside the battery and ultimately become unusable. And then with proper care, those batteries can last a long time and be very useful, very helpful, and they're also safe. So we'll talk about what some of those techniques are as we go through this presentation.
Mostly safe.
Mostly safe, but we'll show you when they're not. Okay? So, and to his point, a battery is a box that stores energy, and if that energy gets loose, out of control, a lot of bad things can happen. So we'll talk about that shortly. So a battery has two different flow pathways. One is what we all know about, which is the flow of electrons from the anode to the cathode, but the other is a path where ions inside the battery are moving from the anode to the cathode as the chemical reaction takes place, and I'll discuss that in just a minute. But what's important to know is that there are two things happening as the battery operates. So each battery has four components. It has an anode, it has a cathode, there is a separator inside the battery that is permeable to the ions that I was talking about just a second ago, but it's impermeable to the electrons. And there's also an electrolyte in the battery. So that separator allows the ions to move back and forth during the chemical reaction, and then the electrons move outside that between the anode and the cathode. So some batteries, like these guys here, this is just a simple alkaline battery, are a single cell. This is a single cell battery, whereas some batteries like this nickel cadmium battery have multiple cells. And this is an example of a lithium polymer battery that has 3 cells. This one has 2, 4, 6, 8 cells wired in series, and these also are wired in series to deliver different voltages and different capacities. The cells in these batteries are wired up either in parallel or in series, depending on what voltage is desired and what capacity is desired in the batteries. Okay, so let's talk about the parts and what they do. So the electrode that releases electrons is called the anode, and in a battery that's always defined as being negative. And then the electrode that captures electrons is called the cathode. And the picture of the battery you can see here is the electrons travel through the circuit, through the load, and do its job. Then there's also, as I mentioned earlier, the separator and the electrolyte. So the separator is really important because what it does is it electrically isolates the anode from the cathode so that when the battery isn't connected to an electrical circuit, it doesn't drain. It's what prevents the battery, it's what helps the battery maintain its charge whenever it's not in use. So, and then the separator then is moistened with typically a water-based electrolyte that is the medium that allows for the movement of the ions during the chemical reaction. So then the electrolyte makes the battery conductive by allowing the movement of those ions between the anode and the cathode, either during charge or during use of the battery. So I'm sorry this is so small here because the picture is slow. But this picture shows in this case, the cathode and the anode separated by a separator that's filled with a water-based electrolyte. And so, and over on this side, in the case when the battery is being used under a load, the electrons are moving from the anode to the cathode, and the ions are moving from the anode side to the cathode. And then during charge, basically that whole process is reversed by forcing current into the battery, and the electrons move in the opposite direction, and the ions move back across. So that's basically how through this chemical reaction, that's how the electrical current is generated. Anatomy of a battery, and in this case, this is basically a picture of a Duracell battery. This is like the batteries that we used to make in those facilities that I mentioned when I started my presentation. A typical alkaline battery is composed of a ring on the, first of all, the outside is a stainless steel can. So these cans are stamped out with the positive end of the battery facing down, and then they are filled with rings that are composed of manganese dioxide. So these machines, when they manufacture these batteries, these cans go whizzing down the assembly line, and they're literally just hundreds of these pieces a minute go rolling through, and these black rings of manganese dioxide are laid down inside these cans. And then the separator itself is paper. So the next step in the manufacturing process is to put the paper separator inside so that it lines the inside surface of the manganese dioxide of the battery. And then the battery is filled with a water-based solution of potassium hydroxide that contains what we call spun zinc. And what spun zinc is it was fabulous to watch it made, is we in the factory had large ingots of zinc that were dropped into a kiln, and then the zinc was melted and it went flowing down a trough. So if you remember the Terminator 2, it looked like this stream of metallic zinc that was flowing down the stream, and then it was dropped onto a rotor that was spinning, and it used to spin the zinc, and then it spins the zinc into little small particles that are then picked up at the bottom of this, the inside of this spinner, and suspended then in this aqueous potassium hydroxide solution. So basically the center of the battery is this spun metallic zinc with the manganese dioxide on the outside. And then what happens is a plastic separator is put in on the bottom, a protective cap, and then the bottom of the battery here has attached to it a pin that goes up through the center of the battery that's pushed right into this aqueous solution of potassium hydroxide and zinc, and then the whole thing is sealed up by a machine. So that's what basically makes up the battery. So again, all the pieces of the battery here are the inside, the zinc anode, the manganese dioxide cathode. The anode and the cathode, you can see, are insulated from each other by this plastic cap on the bottom and the paper separator in the middle with the electrolyte solution in the middle. So that's what makes up an alkaline battery. And then all the rest of the batteries that we talk about are all going to be variations on the same thing, on the same theme. There's going to be, each battery chemistry has an anode and a cathode and a separator and an electrolyte. Okay. So, any questions about that before I move on? I'm going to move on and talk a little bit about how we measure the parameters of a battery. So the first thing we all know about is voltage, and we know that voltage is the potential difference between the positive and negative terminals of the battery. And those measurements vary depending on, if we were to put a voltmeter on here now, we would measure a relatively high voltage. If we put the battery under a load, that voltage will drop. And that's the sort of the nominal operating voltage of the battery, and that's the voltage that we're interested in. We also measure the capacity of batteries in terms of amp hours. So it's either milliamp hours, mAh, or amp hours. And that's the amount of energy at the battery voltage that's stored to run an electronic circuit. So, for example, this battery here is an 11.1 lithium polymer battery that's labeled as having 2,200 milliamp hours. So what that means is that if you run this battery for 1 hour, you should get 2.2 amps worth of current out of it. And I'll show you a tracing in a second from a battery like this. It shows it's a pretty accurate measurement. Okay? So capacity is measured in amp hours. And then another factor is what's called internal resistance. And so it turns out that every battery behaves as though it has a voltage but also an internal resistance. And this resistance in a battery always results in a drop in the voltage that the battery can provide. And the resistance that's in a battery depends on how big it is, what its chemistry is, and so forth. The reason for mentioning it here is that particularly for rechargeable batteries, oxidation products build up inside the battery, and over time they increase the internal resistance in the battery, and as that happens, the capacity of the battery decreases over time. So that, from a practical point of view, is why we're interested in that. And then finally, the C rating is the output current capacity in relationship to the total capacity. So there's this number called C, and if I come back to this, this battery here, this battery is marked with a 30C rating on it. What that means is that you can theoretically run this battery at 30 times its milliamp hour rating. So 1C would be to run it at 2.2 amps. 30C is 30 times 2.2 amps, which is a stonking lot of power, and of course it would only be for a relatively short period of time. So you see batteries with 5C, you see batteries with 20C, you see some with 50C. For guys who like to fly radio control models and they want a big blast of power to get a helicopter into the air or something like that, they want batteries with a high C rating on them. So that's the discharge C. There's also a recharge C. It's recommended typically that when you recharge a battery like this, you don't force current back into the battery much greater than 1C. So if you're to charge that battery, to charge it at 2.2 amps is about amps per hour is about the right rate of charge that should be used for a battery at that time.
Is there an advantage to a lower C value?
Well, they tend to be cheaper, so they cost less. It all depends on what you want to do. If you have a situation where you don't need a big blast burst of energy, like you do when you're flying like a radio-controlled helicopter or a drone, you don't need a high C rating.
For lights or something like that?
Lights, again, no. Assume under the assumption that the current draw of a light is fairly low, and you want the battery to run for a long time on a low current draw. Yeah. Okay. So what do the parameters mean? If we think about voltage as the pressure, so equivalent, so to speak, to the height of the water level in a barrel, and the size of the barrel representing the capacity. The point here is that you can have a barrel that has the same voltage, but you can have a battery with the same voltage with a higher capacity, or you can have a battery that has twice the voltage but the same capacity. So if you, on these battery examples I have here, this is 11.1 volts, 2200 milliamp hours. This is another 11.1 volt battery, 1250 milliamp hours. This one is 7.4 volts at 1000 milliamp hours. This little guy here is 3.7 volts, 400 milliamp hours. So they come in all different sizes and shapes and with different connectors. So maybe I'll pass some of these around so you can take a look at them.
What kind of polymer?
These are lithium. These happen to be lithium polymer batteries. Okay. Any questions about that? Yes, sir.
I was just looking at the lithium-ion battery in here, and aside from the milliamp hours and the voltage, it has 12 WH.
That's a lot of hours.
A lot of, okay.
Yeah.
Why did I think of that?
So that's watts per certain number of hours that it would provide. Okay. And then I came across this when I was getting ready for this presentation. I thought it was kind of interesting. This is a graph that shows what the status of the current battery market is right now. It turns out that the biggest seller on the market are the lithium-ion batteries, and guess where those are? Those are all in your cell phones, exactly right. Yeah, cameras, and we'll talk about those in just a second. Even in this HT now, this is my newest handheld radio. It actually has a lithium polymer battery in it, whereas this boat anchor, which was my first HT, has a nickel cadmium battery pack in it. It weighs more than the entire radio that I have now. The other biggest amount of batteries are the so-called starter batteries. These are the flooded lead acid type batteries. And then in here somewhere there are deep cycle lead acid batteries and stationary lead batteries. So if you add all of those up, the good old lead acid battery still has a pretty huge percentage of the market.
Still using submarines and aircraft carriers.
Everywhere. Invented in the mid-1800s. So, you know, it's a technology that's been around a long time and still being used.
And phone exchanges.
Yes.
Keep going. You know, they're used everywhere is a great point. The other big battery use is our good friend the Alkaline Batteries. So this is you know, the disposable battery that's used in our machines, and then the rest of the battery types are used in different operations. All right.
No listing at all for the old zinc carbon?
I thought about talking about the zinc carbon. I decided not to bring it up because their capacity is so low and they're so almost unavailable now. I didn't bring them up. But what he's mentioning is the old zinc carbon battery is what I remember as a kid, you know, the old Mallory batteries, and we used to saw them open and pull the carbon rods out of them. You know, we used to play around with those when we were kids. But
well, why not talk about the lemon and the zinc nail then?
I showed that one already. All right, so what I've listed here are batteries of interest to amateur radio. They're in an order not necessarily by heaviest use. They're just ones that so they're just here to talk about basically. So I've spent a fair amount of time already talking about alkaline batteries. They represent about 80% of the manufactured batteries in the U.S. So a big bunch of these batteries. So there's literally billions of units that are sold, as I just described. Nominal voltage is about 1.5 volts, but as I mentioned, so that's when you measure it, not on a load. When you put these batteries under a load, typically they read about 1.1 to 1.3 volts, and you can discharge it down to about a volt, and that's when they're done. Their capacity runs about 1,700 milliamp hours, maybe to 3,000 milliamp hours, depending on the size of the battery, or the quality of the battery, I should say. The chemical reaction is, as I mentioned, it's between zinc and manganese dioxide, and my little arrow is moved here, so that's the chemical reaction. Now, it turns out with regard to charge that these are not meant to be recharged, and in fact, if you put them in a battery charger, oftentimes they'll leak, so it's just not a good idea to try to charge these things. One of the things that I bring up here is that again, another little measurement that I think is kind of interesting is this power density. This is an indication of the amount of power in watt hours, coming back to your question a little bit earlier, per kilogram of battery. And you'll see that these batteries, for the amount of power that's available, are actually pretty heavy. When we get into the lithium poly batteries, this number can be as high as 250. So there's a lot of weight that goes along with many of these batteries. And one of the reasons everybody likes the lithium batteries is that you can get a lot of power out of a relatively small form factor. Self-discharge, they're really stable. If you put them in a cool place in your closet, they have a shelf life of between 5 and 10 years. So they're really good if you buy good batteries. And then one of the battles we were fighting all the time in Duracell was how do you dispose of these things? These are completely inert. They can go in a landfill and they don't cause any problems in a landfill because they don't contain any materials that have any significant environmental liability. And unfortunately, when they're done, there's not a lot of good uses for them. About the only thing we could find to recycle and reuse them was to grind them up and contribute them to the production of asphalt that got laid on the highway. So they're a bit of a challenge to get rid of whenever they're all done.
Which could explain why they are the most sold you've got to replace them.
Yes, well, that's, but people want disposable batteries that they don't have to mess with and try to recharge either, and so they're a good balance. And I'll talk about battery research in just a minute. It's a real challenge for us. This is the discharge curve from actually some of these batteries. I ran these just before I came over here tonight, and I'll talk about it in a second. I use this little instrument right here to make the battery. What this thing does is what this does, it provides either a constant discharge current, and what you can do is you can measure the energy capacity of the battery. So what's shown here is the voltage measurement. So I had two of these in series. So you know the nominal starting voltage of these two batteries should be about 3 volts, and if you look close here, you can see that there's a little bit of a red line that starts right up here. And so that was the starting voltage on this, but as soon as we put it under load, the voltage dropped. So this is the voltage, and in this case it happened to be a 1/2 amp load. And this shows then the tracing over time until I got to the point where it was to the discharge point of the batteries, 2 volts, which is 1 volt plus 1 volt with these two series. And what you can see is down here the total amp hours is about 0.28 amp hours. So if you remember that, I'll compare that to some other batteries here in just a second. So anyway, this shows you the discharge curve of the battery. One of the things to note here is that with these batteries, when you put them in something, they drain, and you can see that the drain, it's almost linear, and when it gets to the end, it comes to the end. There's no sudden crash in voltage at the end, which is important to know because other batteries don't have the same behavior, and I'll show you that in a minute. Okay, so typical uses of alkaline batteries, they're used very general purpose, deployed in a broad range of consumer products. You can just buy them everywhere and use them, as we've already talked. They are not rechargeable, and they're generally available. Okay, so then the next type of battery that is sort of a replacement for these, or an alternative to the alkaline batteries, is the nickel metal hydride battery. And I got a whole bag of them here because I like using these things. These are rechargeable, so they are the sort of the rechargeable equivalent for the alkaline battery. They have a different construction. They have what we call in the business the jelly roll, where the anode and the cathode and the separator and the electrolyte are rolled up into this, so to speak, jelly roll, and then that jelly roll is stuffed up inside the can, and the electrical circuitry is completed inside the battery. They have a little bit lower voltage than a typical alkaline battery. Typically they have a much greater capacity, which I'll show you in just a second, than a typical alkaline battery. And that's why I like them. If I look at the capacity, I like these because when I use a AA battery, nickel metal hydride, it lasts a lot longer than a typical alkaline battery. Plus I can recharge it. Its power density, they're a little bit lighter than the alkaline batteries. And they actually, depending on the type of the battery, some nickel metal hydride batteries lose their charge if you don't use them, so you have to constantly keep them charged up. There are some batteries that have a longer life. And again, they're fairly safe to dispose of in a landfill. Typical uses, greater capacity than alkaline batteries, sometimes 2 to 3 times the capacity. Question? Oh, I see. Okay, all right. I know that. I'm watching. And they're readily available. This is the discharge curve on the nickel metal hydride battery, and this is the overlay. The green line here is the alkaline battery versus the nickel metal hydride. So you can see that it has a greater capacity than the alkaline battery. Nickel cadmium batteries, I won't spend too much time on them because they're passé now. This is an example, a couple of examples of nickel cadmium battery packs. They're not used so much anymore, most because of their environmental liability. Particularly the cadmium is not a good thing to dump in a landfill, and there are other alternatives that provide power and an advantage that they don't have. It also turns out, I was doing a little bit of research about this for this presentation, and we were talking about it before the meeting. It turns out that there is this concept of memory that's associated with nickel cadmium batteries, and apparently it's not true. So, but I haven't really tested it. I don't know. But anyway,
No, you're correct. It isn't true.
it's a myth.
This is what I came across.
Okay, let me move on because I want to talk about the lithium-ion batteries. The typical cell of the lithium-ion battery, and a great example of the lithium-ion battery is the batteries that are in your cell phone, or this is an example of a lithium battery in the back of this. I'll get it open. And I know time is not my friend right now. This is a lithium-ion battery pack that's in the handheld. These are rechargeable batteries. They're really great because, as I mentioned a little bit earlier, they have first of all, they have good high voltage, and they also have a power density such that they're lightweight with a lot of power packed inside. And again, disposal is pretty straightforward because there's not a lot of toxic materials in them. And actually, the metals that are in many of these batteries have some value, so there's a fair amount of recycled value. So we want them back anyway, just because of the metal value that's in them. Typical uses for lithium-ion batteries is, as I said earlier, they're lightweight, high energy density. You can connect many small batteries in a circuit, so like those lithium polymer batteries, they can be put together in battery packs. And their uses are in portable devices, power tools, electrical vehicles, aircraft, all kinds of uses, and largely replacing the nickel cadmium batteries that I mentioned a minute ago. And then finally, the lithium polymer batteries, their nominal voltage is about 3.7 volts. I passed those around a little bit earlier, so in a typical battery pack, multiple numbers of those cells are put together to build packs of either 3 volts or 7 volts or 11 volts and so forth and so on, in different sizes, different form factors, and different milliamp hour capacities. Again, a lot of power density in these things, as much as 400 watt hours per kilo, which is pretty amazing, which is why they're most commonly used in radio-controlled aircraft. Their discharge cycle looks like this. So what happens is this was an 11.1 volt pack that was rated at 2200 milliamp hours. And what you see is that the voltage continually drops across its use, and then it just falls off a cliff. So if you're flying a radio-controlled aircraft, you want to get it on the ground before this happens. Okay, so that's the big watch out with these batteries. Interestingly enough, this battery stopped right at 2200 milliamp hours, which I thought was pretty good. It showed that the labeling on the battery was pretty good. So typical uses: radio control cars, aircraft equipment, personal electronics, and so forth. The big problem with lithium is that metallic lithium goes bang if it gets in the atmosphere with water. And these are a couple of examples. This is a smoking lithium polymer battery pack. We've all heard about computers going up in flames because of lithium batteries. And you remember the problems that the Boeing 787 had in its early days. It was all related to the use of these lithium-ion batteries. When I worked for Duracell, we made lithium batteries, and it was really cool because they were all made in dry rooms. So you had these massive factories that had relative humidity rooms of like 0%, because when the jelly rolls that I was talking about a little bit earlier are made out of these big long ribbons of metallic lithium, and if you get them in the atmosphere, they make a hell of a fire. So we did all of this in dry rooms and sealed the cans of the batteries, and then brought them out in the atmosphere.
The lithium itself, is it brought in under oil or anything?
Say again?
Is the lithium brought into the plant under oil?
It's all wrapped, and inside
Sealed?
it's all hermetically sealed bags in these big ribbons. It's amazing to see it. It's so cool to see these ribbons of lithium come rolling off the spool, literally like this. This is what the spools look like. So pretty amazing. And like I said,
What's the width of the ribbon there?
it depends on the battery. On these, this is fairly narrow, about an inch or so, and I've seen it as wide as 2 inches. So it depends on the size of the battery that you're making. Sealed lead acid batteries. My clock is running out here, so I won't say too much about them other than, as you saw earlier, they're the workhorse battery of our business. typically used for storage, starting, that kind of thing. I can say a little bit about disposal and landfilling and recycling. There's all different kinds of battery chargers. The one thing that I'll say about battery chargers is it's really important to use the battery charger that is designed for the battery. So if you use a nickel metal hydride battery charger on lithium batteries, you'll have a fire. So be careful. There's some interesting test equipment. Maybe we save it for another time to talk about that. I like messing around with this stuff, so I have one of these battery testers. And then finally, with regard to battery safety, stored energy, lead-free and out of control is not a safe thing. So there's some precautions you should take. Basically, what I'll say is follow the directions that come with your batteries, and you'll be okay. Battery advancements, as you can imagine, there's a tremendous amount of research that's going on. Maybe my parting comment that made me smile is I was having lunch one day with a guy who was doing battery research at Duracell, and he said, you know, Leon, doing battery research is really tough because there's not many R&D programs that are limited by the periodic table of elements or the size of a stainless steel can. So I'll leave you with that one. There's a lot of challenges with making batteries because the chemistry has to be reactive, and reaction isn't stable, and there's just all kinds of interesting problems and fascinating problems with it. So for a kid like Jacob, there's going to be a real opportunity in developing energy storage for the future. So with that, thank you very much, and I'd be happy to answer any questions.